All right, today we're going to keep on working on trying to figure out how to deal with the quadratic equations and how to read the equations, different values as they change, what it means to the equation, means to the graph, stuff like that. Okay, so let's take a look at this, writing quadratic equations. Okay, today we're going to look at determining what the quadratic equations looked like based upon charts and graphs that were given, more so the charts really than the graphs. And this is a little bit different. Okay, some of the stuff is gonna seem a little bit the same. That activity that you did on Thursday where you had the different cards and you had to match up the equation and the graph and the little description and the domain and range. Some of you didn't get the idea of that. Some of you just said, "Ooh, this one has a 7 and this card has a 7 and that card has a 7," and we just kind of matched up all the cards that had a 7 rather than really figuring out what the equations did and stuff like that. Today you're going to have a better understanding of it. Okay, and we're just going to jump straight into some examples. There's really nothing I can tell you except kind of guide you through how it works. Okay, so let's take a peek here. Example, if a parabola had the following points on it, and we're provided with a chart that has several points, okay, and some of you guys have figured out that, hey, once you have the equation, our calculator's chart can give us all kinds of points. Okay, so we've been looking at those points and stuff like that. Now we're in a situation where, hey, they did not give us the equation. Okay, they give us some points that are on there. And the question we're going to be trying to answer today is based upon these points that they provide us, does it take the form, okay, of just the regular parent quadratic function y equals x squared, or does it have a vertical shift to it like y equals x squared plus c? Or does it have a stretched or compressed part of it, like y equals a x squared? Or possibly does it have a shift and a stretch or compression, like y equals a x squared plus c? So what we're going to have to learn to do is probably what some of you have been trying very desperately to avoid. We're going to have to learn how to deal with these equations without just going to the calculator, typing it up, and looking at it, because now we don't have anything to type up. Okay. Well, there's a couple of things we're going to have to look for. Okay, we're going to have to check it for a possible vertical shift. Okay, to see which equation it might be. We're also going to have to check it to see if maybe it has been stretched or compressed. Okay, so we're looking to see if we can figure out what might be going on with the variable a and what might be going on with the variable c. And I'll tell you in as easy a language as I can think of how to look for that stuff. Okay, now the easiest thing to look for, okay, is what I'm going to suggest that you look for first. Okay, start with the easy stuff first. And that's to look into the chart for a possible vertical shift. Okay, so we're going to start with that. Now, the regular parent quadratic function, okay, y equals x squared, where does it cross? Okay, where is its line of symmetry? Okay, remember how the parabolas, they're the same on either side of the equation? Okay, the parabolas, they have a line of symmetry, right? And when they haven't been moved, okay, when they haven't been moved, where do they cross the y-axis at? Like when they come down and they cross the y-axis, where is it? Does it cross down like on the negative y-axis, at the positive y-axis, or is it at the origin? It's at the origin. Okay, that's where the parabola is supposed to cross at when it hasn't been messed with. Okay, so that's what we're going to do first. We're going to look at the graph and we're going to see if we can decide, does it cross the origin like it should or not? Okay, we'll have a look at your chart. Does it cross through the origin? Okay, we got a point right here, right? Okay, it does cross through the origin. Okay, so the answer to the question is, does it have a vertical shift? The answer is no, it doesn't. It has not been moved up or down because it's still passing through the origin. If it had a vertical shift, it would be crossing the y-axis somewhere else. Okay, so what that means is when we're looking at those four equations that were at the bottom of the screen, on the first screen, we must be looking for one of the ones that does not have any vertical shift. So out of those four, we can eliminate the two that have a plus C. attached to them. Okay, now the next thing is a little bit more complicated to check for, but once you get used to it, it's not that bad. Okay, we need to see if it has possibly been stretched or compressed, because that's going to tell us whether it's got that coefficient a or not. Okay, now the parent function is y equals x squared. If we have not messed with a graph at all, that's the parent function, y equals x squared. Okay, and that means that the coefficient of x squared is supposed to be 1. Y equals 1 x squared. Okay, now, unless something has been changed, that coefficient should be a 1. What this means is, as the x value moves, okay, a number of steps away from the line of symmetry. Okay, the line of symmetry is sitting right there where the graph crosses the y-axis. As we start changing the x one step away, that's going to move one step to the left and one step to the right away from the line of symmetry. And we can continue to take more and more steps away from the line of symmetry of the parabola. So as x moves a number of steps away from the line of symmetry, the y value should change by the square of that number of steps. Now, it may sound confusing, but I'll show you what it means here in just one moment. Okay, now let's look at our points here. Now, where is the line of symmetry at? We ought to be able to look at the points and see where it's kind of doing the same thing, moving away from a particular place in the graph. Well, where is it? Okay, we haven't really moved our graph away from the y-axis yet, so wherever it crosses the y-axis should be good. Okay, and you can tell that it's the line of symmetry because look what happens to the values on either side of the line of symmetry. It's the same set of values as you move one step away, 2 steps away, 3 steps away. It's matching up on either side of the line of symmetry. Okay, so looking in the chart, you can actually kind of quote unquote see the line of symmetry by looking at the points as it moves away from it. Okay, so there's the line of symmetry. If this were a graph, that dotted line right there would be splitting our parabola right down the middle. Okay, so there's the line of symmetry. Now, if x equals 0, okay, is going to be where our line of symmetry is at. Okay, then as I said, we're going to compare our points going in each direction away to the parent function. Okay, now the parent function is supposed to move, okay, uh, when you move one step away from the line of symmetry, okay, when x is 1, if you plug in x being 1 right there, what do you get from y? Y equals 1 squared. That would be 1. Okay, if x is 2 steps away from the line of symmetry, what does that do when you plug it in? Y equals 2 squared. That would be 4. So you can kind of follow this idea that as you move one step away from the line of symmetry on the x-axis, that would be 1 squared on the y-axis. 1. As you move 2 steps away on the x-axis, that would be 2 squared, which would be 4. If you move 3 steps away, that would be 3 squared, which is 9. Okay, we ought to be able to use this same information to compare it to any other parabola and see what it does. Okay, so let's look. Here's our line of symmetry. As we move one step along the x-axis in either direction, does it do what the parent function does? Okay, how many steps is it to move from here to there? How many units did it change? Changes 2 units, right? This is a change of 2. This is a change of 2. What was it supposed to be in the parent function? It's supposed to be a change of 1. Okay, so what does that mean to this graph? Okay, it is moving by bigger numbers than it's supposed to move. That's a change of 8. That's a change of 8. What was it supposed to be in the parent function? Change of 4. Okay, so what do you think about this graph? Is it compressed? Is it moving slower than it should? Is it stretched? Is it moving faster than it should? Look what's happening to the y values. Instead of moving by 1, and 4, like the parent function does, it's jumping up by 2 and by 8. Okay, this graph has been stretched. Okay, so look one row up and one row down. Does one step on the x-axis make 1 squared steps on the y-axis? The answer, no, it doesn't. Okay, it's not making 1 squared. Instead of getting a 1, we got a 2. Instead of getting a 4, we got an 8. Okay, so this graph is in a bigger hurry than the parent function, which means something has changed the speed of the graph. Okay, so when it comes back down to our equations, picking out which one it was going to be, well, we'd already crossed off the second one and the fourth one because we knew we weren't going to have a vertical shift. But we're also going to can now cross off the parent function because we know that it's not stepping by the right amounts. It must have a coefficient in front of that x squared. As a matter of fact, it's moving twice as fast as it should. If you wanted to know what A was, it's moving twice as fast as it should. A should be a 2 in this case. Okay, but all we're doing right now is just trying to identify the structure of the equation. Okay, so that would be the choice. Okay. Now I'm sure everybody's at least a little bit fuzzy, if not a lot fuzzy, on this. Okay, so we're going to look at a couple more, see if we can't figure it out a little clearer. Let's look at another set of points here. Okay, if a parabola had the following points on it, would it take the form of y equals x squared, y equals x squared plus c, y equals ax squared, or y equals ax squared plus c? Well, let's walk through the same steps again. Okay. The first thing we're going to check for is to see if it has a vertical shift of some kind. Okay. We'll have a look at these points. Okay, let's think about them for a second. Does this graph or does this parabola have a vertical shift to it? What do you think? Does it cross through the origin like the parent function would? It does not. Okay, look where x equals 0. Okay, when x equals 0, then this information is telling us where it crosses the y-axis at. Does it cross the origin? No, clearly does not. So this one does have a vertical shift. Okay, so would we want one of the equations that has the plus c attached to it? Or would we want one that does not have plus c? Okay, well that plus c is what causes the vertical shift. That's what moves the graph up and down, or moves the parabola up and down inside of the plane. So in this case, we'd be able to cross off the parent function because it's definitely been moved. And we would cross off the third equation as well because it does not show any kind of a vertical shift. Okay, so this time we're working on the second equation or the fourth one. The only thing left to do is to decide, okay, has this graph been stretched or compressed in any way? Okay, so let's take a look at that. Let's see if it's been stretched or compressed. Where's the line of symmetry this time? Which ordered pair in there? The first one, second, third, fourth, fifth, or sixth? That's going to be your line of symmetry right there. How can you tell? Look at the information moving away from the line of symmetry. As you make one step away, one step away. Okay, it's the same on both sides. 2 steps away, 2 steps away. Same on both sides. Okay, so that's your line of symmetry. Okay, now let's look at the step size. Okay, let's look at the step size. As we move away, we're starting with -4. Okay, so what's the change as we go from -4 to -3? How many units change is that? Just 1, right? Okay, so that's a change of 1. Isn't that what the parent function is supposed to do? When it changes 1 on the x-axis, it changes 1 squared on the y-axis. So 1, 1. That's right. Okay. And what's the change as you go from -4 all the way to 0? How many units change is that? It's 4 units, right? Was that what the parent function is supposed to do? As you change two units on the x-axis, it should change 2 squared on the y, which is 4. That's what we got. Okay, and we could even check it even further because we do have an extra point down here. What would happen if you move 3 units away from the x-axis? That would be 3 squared. On the y-axis would be 9. From -4 to +5, that's 9. That is the way that the function is supposed to move. Okay, so it does not appear that the speed of the graph has been changed. It hasn't been stretched, it hasn't been compressed, anything like that. So what we would do is we would select an equation that did not have a coefficient in front of x squared, because the coefficient would change the speed, either speed it up or slow it down. This one did not get sped up or slowed down, had a vertical shift, but nothing else. So we would pick on the second equation there. Okay, I've only got one more here. If a parabola had the following points on it, would it take the form of which one of these? All right, the first question you should ask yourself is, does it have a vertical shift to it? Okay, and it can be helpful to identify where the line of symmetry is, okay, because that'll tell you where it crosses the y-axis. And it looks like the line of symmetry is right across there. It's the same going either direction on the y-axis from there. Okay, well, it's crossing at 0, 5, so I think we would have to say it absolutely has a vertical shift. It is not crossing at the origin. That takes the parent function out, and that takes this other equation that does not have a vertical shift out. Okay, from here, let's just see how the graph moves. Okay, as we change one value on the x-axis, either direction, okay, we should change 1 squared on the y-axis, which is 1. But I think as we can clearly see, while it changed 1 value on the x-axis, it changed 3 values on the y-axis. Okay? And we can continue to check that even further. Since we do have more points, we can check as we move 2 units away from the axis of symmetry there, and the y-axis should change 2 squared units, which is 4. Okay, but from 5 to -7, that's actually 12 units worth of change. 5 to -7, 12 units worth of change. And we could do that even one more if we would like. We've moved 3 units away from the axis of symmetry on the x-axis, so that should mean 3 squared, which is 9 units worth of change on the y-axis, but from 5 to -22 is 27 units worth of change. Pretty clear that everything is triple the amount that it's supposed to be. That means that we probably do have a value. It's probably a 3 in this case because everything's turning out to be 3 times as much as it should. But that's your equation right there. That would be the format of the equation we would be looking for if we saw these particular points. Okay. Well, this is very much what your assignment's going to be like. You're going to be given charts of points, okay, for parabolas. You're going to be asked some questions about those, largely dealing with stuff like this. Does it have a vertical shift? Where is the line of symmetry at? Has it been stretched or compressed? And which equation would go along with that? Okay. So that's all the examples I have. I guess let's get to the assignment.